Hi, hello.
So Zunk was asking about the face file that we created in the previous lecture. So the face file that is used for the location to locate the earthquake. Let me start the screen share. Okay, so you see my Jupyter notebook?
Yes.
Yes.
Okay, so we had this file created, right? So the name of the station, channel, which phase did we pick, and the time of this phase arrival. So basically, when you run this code, okay, just a second. So it runs for me. Yes, okay, it will work, but it will move the screen if I don't wait.
Just stop.
Okay, let's wait that this finishes. Yes, anyway, so the phase file that is used with the non-limlock, the software that is used for location of the earthquake. This is just one of many software packages that exist, but I normally use this one because it has the best, at least for me, ways how to locate. I can show you another one later. So this phase file is actually created in our code. So this window here, when you run it, this phase file should be generated. If you get some error, this is maybe because you do not have an NLL folder. So you can create a folder where you are running the Jupyter notebook from, or you just delete this part NLL and run the code like this, and now this phase file will be created directly in the directory. So if I run this now, this file is here now, so you can see it. But if you have some problem, I will send it to you later. But if you don't have the non-limlock installed, there is no, I mean, you cannot actually use it. What you can maybe try, just a second, let me try to find this quickly. Yes, what you can do is if you want to try, let's say if you tried to install the Pyroco on your computer, you can also use this Lassie. This is another package to detect and locate earthquakes. It does both of the things, and here there is also a tutorial that you can follow and try with your own data, and it's actually very simple. Basically, the main things that you need to set is the surge grid area where you are interested in the earthquakes, and velocity of the P wave and velocity of the S wave, and then you run it. And it will detect earthquakes, and it will give you approximate location of the event. If you are not working with a big data set, it works very fast, and it's quite nice to use. I will put this into the chat. So how do I do this in Zoom? Okay, I've put the link into the chat of the Zoom, so you can find this software. I used it a few times. It's, as I said, it's very simple. Just follow the tutorial. But you need to have the Pyroco installed before. yes, how it works, basically, quickly how it works is that it, let me make some drawing here. So you can see here a trace with an earthquake, and the idea is here that you generate some kind of a function over this trace, let's say STA, LTA. In this, clear, just a second, let me redraw this. So let's see, here in this example, they use this wave packet if but you have different ones. So you can create this function. Let me turn on the annotate back. And this function basically takes your raw data and it calculates, let's say, this IFC. I don't know exactly what it is, but it can also be the STA, LTA, and you can find them here inside of the code which you can use. So basically, your earthquake, your trace with an earthquake will look something like this. And let's say for this trace here, it will look like this. So now how this program tries to locate the earthquake is to align all the traces in such way that they move very close to this defined line, and where this the misfit that is calculated then is the lowest. This is the selected grid where the earthquake happened, the node on the grid. I mean, there is one paper describing this methodology. I think, I don't know if it was published or not. Maybe I think I have it on my email. I can send it to you so you can understand. Let me just quickly search for it. The software is nice because it's very fast and quite simple to use, but if you want to get some really well located events, this is not something that should be used. This is just, let's say, for the first scan of the earthquakes, where if you have them in the data or not. Okay. Yes, I found the paper. I will send you the paper. Okay, so let's go back to. So, does anyone have any questions about the previous lectures before we continue? You should. Let me just prepare the email that I don't forget. Okay, I've sent you this paper, and you can see how this lassie works. Then, if no one has any questions here, what we can try to do now is, so we were talking about the STA-LTA detector last time. So a very simple amplitude or so-called energy detector that, as you remember, you take two small time windows. One is long, one is short, and you calculate the ratio between these two time windows. So now what I prepared here is a very short tutorial first on how this does work, and you will see it's extremely simple algorithm. I mean, you will see most likely, it can be it can be made much more effective than I did it, but you know, since with the time I had, this was the only way I could do it. So here you can see the function called STA-LTA, and inside of this function you put your stream of the data, the length of the short time window and the length of the long time window. And then we, inside of this function, we generate an empty list to which we will append our ratios. So with OpSpy and Python, this is very simple to implement. So there is a function in OpSpy for the stream element. You see here this dot slide. Here in this slide, what you do, you put the length of the window in seconds and the step that you want to do. So let's say if your data is 20 seconds long and you create a window with long 10 seconds with step 10 seconds, then you will have two successive time windows, first 10 seconds and second 10 seconds. But if you put a shorter number here, so let's say 1, you will take first 10 seconds and then you will move for 1 second further in time and take these 10 seconds and so on. Basically, so now we generate this long time window of our stream for the long time average. So this is now our LTA. And because if it's average, we need to calculate the average of our selected data. So this is now our selected data, and the NumPy, this NP, this is short for NumPy that we imported here. NumPy has a simple way to calculate the average of array. So this is now our mean, the long time average. We can do the same for the short time average. So we take the mean of the slightly complicated way how I wrote this, but basically this part is long time window. So this one here that we selected, but with this part here, I say that I only want to take the last values, the last, let's say if we want to take only 5 samples for the short time average, I take the last 5 samples of this long slide window. This is defined like here. So here I could write this as, yes, here, if I don't put anything before this double point, this means take everything up to here. So this means the first few samples. I could do this a bit more complicated. I even tried to do it, but the ratios that I got were a bit strange. So I just said, let's simplify this and try to run it like this. And then we take the ratio between these two, so the STA over LTA, and finally we append this ratio to our list. And at the end of the function, we return the NumPy array of this list. So we can try to run now this example to see what we get. I will read the data that I already have downloaded. And now I filter this data between 2 and 20 Hertz, select only one station and one channel, and cut it on a time window around the earthquake. So, you know, I just want to do this on one trace so it doesn't get too complicated. So now this is my, just a second. This is now my earthquake, and you can see that here before there is something, and maybe here and here. This could be some, I don't know, maybe foreshocks, some aftershocks. And now I can calculate this STA over LTA. So I generate this CF, I take my stream, and I say, okay, I want to take 5 seconds for the short one and 20 seconds for the long one. Let's see. I run this. It works. Now I will make a picture of it so you see what is happening. So this is the recorded signal, and this is our short time average, long time average ratio. So you see that it's not completely stable, and we have a lot of spikes. Why? We can check later what we see there, but basically, if we just concentrate on this earthquake here, you see we are detecting it with this spike here. Because I wrote this function in a very naive way, you know, you would maybe expect this to be much bigger than this one here, but you know, yeah, you can. This is maybe because I take the first data. Let's see if I change this to the last few samples. Of course, this will change. Let's see how this picture changes. Not much, okay. But what I could do is change, let's say, this to 1 second and leave this at 21. What happens then? You see, I get much different spikes because I set the configuration of our detector in a different way. If you remember, I told you that, let's say, for local earthquakes, you need to have you need to test your detector with many samples to see what is the best way to select this long time average and short time average window. The same if you want to detect teleseismic, so far away earthquakes, large earthquakes, you need to set this in a different way, and so on. So let's put this to 5 and 10. What happens then? Yes, it gets very messed up because these two windows are now very close by. Time. So somehow for these local events at these distances, this should be the best configuration. But of course, the STA-LTA is already implemented in OpSpy in a much more sophisticated way. So if you want to detect earthquakes with STA-LTA, just please use the function given already in the OpSpy. But this is just, you know, a short visualization how some things are very simple to implement.
Professor, with figure blue,
yes.
Why when earthquake happen, we have blue light shorter compared with the before earthquake happen?
With this one?
Yes.
Yes, I hope I will explain this with the next. So let me, here I take this slide function and I create 1 minute long signal with step of 1 minute. So I just, you know, cut my signal to 1 minute pieces and I will plot them. And so let's look at it. I think this is because of maybe let's change first frequency if we can see something different. No, it's completely shifted. I think I have some problem in alignment of the back to here. So one thing is that let's say before this earthquake, we have, you see these 4 shocks. This is one very small one, slightly bigger one, slightly bigger one, and slightly bigger one. You see, and this will really make our detection behave in a strange way because we set it for such small earthquakes. So maybe this spike could be because of this. this is the only question answer I have for you now. I really did not, to go too much in detail here to understand this, but I think it's because of this 3 or 4 earthquakes that happened before, and because of the time window that we selected. I don't know exactly what happens here, but maybe let's try to change this slightly to see what happens if I select a time window somewhere in between. Okay, this is
No,
I think fine. Much better. Yes, because as I said at the beginning, here I select. First try was I selected the first samples of the long time average, then I selected the last samples, and now I took some samples in between. In what I should do is I should also make a slide window of this short time average within the long time average. This would be the correct way how to implement this, and then most likely we would get much better this function, but otherwise, yes.
Professor, and how a ratio between a short time window and long time window relative to earthquake?
This is because let me make this like here. So let's say we have our signal of this is LTA signal, okay? Our signal of noise will look like, I don't know, something like this. Let's say the noise is always the same, it's straight line, okay? And then the average of this should be what? How long is this? And so sum of this divided by the length, okay? So something, x. And our short window will be just this 3, so this 3. And then let's say next 3, and then next 3, and so on. So this ratio will be something. But as soon as we have but as soon as we get an earthquake in our long time average, our signal should look so something like so something like this. So our average changes quite a lot, right? But because for the short time average, we are taking only few samples, the average of this one will be much higher than of all this. And this is why the ratio, is the one that, this is the ratio then between these two values, these two averages. Do you understand? Maybe just a second, where is?
Do you mean with short time window, we will use average of this?
Yes, average of short and average of long time window.
So, and long time window, you also will you average?
Yes, both. Okay. It says, I mean, the where is this?
Just
the STA stands for so it's short time average over long time average.
Yes, okay.
So it's always an average, and in a correct way, implemented in a correct way, we should get something like this for P and S arrival. Okay, but this is longer in time than the one that we are looking at. So, and much better implemented than what we did.
Yes, thank you.
Okay, so any other question about this STA, LTA? Okay, then let's look at the match filter detector. So if you, so I showed you some slides last time. Let me just open the slide again, try to find it. Okay. Okay, let me just find the slide of the cross correlation. So let's say this one. So, or let's go from the beginning. So last time I told you a few words about this match filter detection algorithm. So an algorithm where you take a template of your earthquake. So you extract your earthquake, a known earthquake, and you try to use it as a template to scan through all the data that you have and calculate the cross correlation value between the window of your earthquake and the selected window of your continuous data set. So as I said, to make this fast, you need to first downsample the signal to, let's say, 20 Hertz, depends on the frequency you're interested in. And then you extract the windows around P and S, or only S as you want. And then you also filter the signal, and then you compare this to the continuous waveform. So here in this example, we have this blue is our template, and here are this cross correlation values. And you see when we get to some part which is very similar to our template, this is the start of the template, and the calculation here shows high cross correlation. This will, show up like a spike here. And here, when the template looks almost exactly the same as the continuous signal, the spike, of course, is much higher. So basically, yeah, okay, let me go back to the Jupyter. So basically now we will try to look how this is done. Also, you can use OpSpy to do this, but with OpSpy you need to make a lot of changes to the code if you want to run this very efficiently. But there exist many packages that are able to do this. So let's say one example is this one. It's called AQ Core Scan. So correlation for earthquakes detection in Python. So on this website you can see how this works. There are even some tutorials, so you can try with your own data. Everything is writing down the code, so you will have to try a bit. Let me see. Yes, okay, here let's say this is example of the templates that were used for this tutorial, and then you can see you can make such plots, how many earthquakes you detected newly, and so on. I mean, it's a very, very powerful method. Let's say if you are given an earthquake catalog from some institute that already checked this data, you can run this match filter and you will be able to detect many more small earthquakes that were previously missed because of the way how the institutions work. Normally, they do not check continuous data sets for each day because this is too much work. So, for each network that there exists, there is a lot of opportunity to explore the data in such ways. What at the end, what you will get, let me open something. I can show you the example from our recent paper. Okay, so let me open this picture. So at the end, you can get something like this. You can imagine. So I took, for this paper, we took, do you see the picture?
Yes.
Yes, yes.
Okay. So for this paper,
Yes,
we
yes.
only took these red earthquakes that you see here and the red ones that you see here. We took them as templates and we scanned the data. You see all this data, all these years of data that are available here. And all these blue and yellow and green earthquakes that you see here are those that we detected by only using few selected earthquakes. So for the input, we used, I think, around 2,000 earthquakes, but altogether we were able to find almost 50,000 very, very small earthquakes. So it is very, very powerful method. Anything else here? No, okay. So the match filter, as I said, it's very simple again to try it with your data sets. Where is my Zoom now? Today I have some problems with my computer. Okay. So let's do the import here and here. So yes, as I already mentioned, so the cross correlation detector are very good for this detection of very low signal to noise ratio events of very small earthquakes. And you will see in this example what we can detect. So here I will send you this data so you can try with different examples. So let me read this data. So what I do here, it's taking some time. Okay, but let me start from the beginning. So I read in the data and I can plot it here. And you will see I have, this is something that you will see quite a lot of times. Let me make this like another graph. Oh, okay, here it's not visible, then never mind. So a lot of time your data will not be very nice. Let's say you download the data from one station and there are some problems within this station. Let's say internet connection stops for 1 second, or I don't know, electricity goes out for 10 seconds. So you need to pre-process this data quite good. So you see, if I just read in the data that I have saved, I get 4 different traces here, even though this is, you see, always the same station and always the same channel. So basically, this means that we have a continuous recording of our data, but it looks like this, and then there is a gap and another gap and another gap in our data, you see. So it's made out of 4 parts, even though this is one single day of data. So first, what I have to do is call this merge function on our data. So this function will put these things together. So these holes will not exist anymore. There are many ways how you can do this. One way is, let's say, to just put zeros in these holes. But then when you filter the data, you can get some problems with strange signals. Let's say if you filter something with zeros inside, the filtered signal will look like this. So it's better to, maybe not use this with zeros. You can use it with 1, with anything, but then your signal might look like this, which is, again, not something we want. So I think, let's say for this match filter detection, the best way is to use this interpolate function. So basically, it will take our data and take the last sample and the first sample of this missing part, and it will interpolate with some random signal inside. So if you look at the data after the interpolation, you will not know there was a hole here in time. Okay. So okay, now when I call this merge, now I will get only one picture here, not 4. And I will resample this to 20 Hertz. This is, remember from the slide before, I downsample the data from 200 to 20, so everything will be a bit faster. And in the last step, I filter this between 2 and 8 Hertz because I'm looking at small local earthquakes that has the biggest energy here. So I read this data now. It takes some time because it needs to do this interpolation and the resampling. Okay, now if I plot this, you can see this is my one day data now. And you can already see I have many earthquakes happening on this day of data. So now let's first try to detect some of these earthquakes with this recursive STA-LTA method that we already tried. And let's see what I detect. Okay, so all these blue lines are our detected earthquakes. And also this is what I took from previous code. So I try to extract this blue. I run this, okay, I get 286 different detections. Okay, let's make this higher so we don't get too many. Still too much. Okay, let's try to plot 43 earthquakes. Let's see what this is. And you already see we have plenty different earthquakes happening. So why I selected this example? Well, this is because not far away from this station, a few days before, there was a large magnitude 6.5 earthquake, and all these earthquakes with long signal, so like this and this one, these are the aftershocks of this faraway earthquake. I mean, far away, 100-kilometer away earthquake. But then you see that inside of our database, our detected earthquakes, we also have this short duration earthquakes. This one, and these are actually very local earthquakes. And I took the catalog of this region, and I was only able to find 10 of them, I think, in the catalog. So even looking at this picture here now, I have what? 1, 2, 3, 4, 5. Yeah, this is not an earthquake, this is an artifact. So I have 5 in this, which is, let's say, comparable to the catalog, the one that I downloaded from the internet. So what we can do now is we could extract this kind of earthquake and generate a template out of it, and scan all the data which is available. I mean, all the data, try to detect many more of these small ones. So this extraction, let me go here. Okay, I will, just I need to set here the previous values. Okay. So I will select 2 of these earthquakes that happen close by. So I checked, and here the timings that I give here are manually selected from the data. They are not calculated or anything. So I create a template 1. So I take my detections here and cut it, and I can check how it looks like. So you see, this is my template earthquake, and I create the second one here. And this is my second earthquake. You see, they are not the same. These are 2 different earthquakes. And then I can go. So OpSpy has already this correlation detector implemented inside. So you can try to run it. And what we will say is that, okay, let's try to detect, using these 2 templates, everything that has a correlation value of at least 80%. So we will take our template and move it in very small steps over all this 24-hour data, and let's see if we can detect something. Let me run this. Yes, okay. With the template number 1, we were able to detect few earthquakes. You see these orange lines are those detections. This is the cross-correlation value of 24 hours calculated, and you see these are these spikes when the cross-correlation value is high. And because we set 80%, we take everything that is above. This is for the second template, and you can see. So in this example, I took only 2 templates, and I was able to detect almost 5 times more earthquakes. So let's say in the catalog that was given, that I downloaded from the internet, I said there were 10 earthquakes in this region at that time. So after using those 10 earthquakes as templates and some more that I found myself, I think I was able to find around 200 very small earthquakes. And currently we are working on a paper about this because it's an interesting region. So let's see. We take our detections and we can try to extract this 9. So you see they look very similar to our template. Where is it? Which one? Okay, I can maybe do the. So you see this one and this one and this one and this one, they are all very, very similar, especially around this S wave. Here, this one, you see that the magnitude of this one is most likely higher than of this one because we have much more noise here in the front. and all the rest. So you see, we can really detect a lot using this match filter. I can lower down the cross correlation value, let's say only 50%, what we can detect now. Let's see, oh, we detect a lot, but I guess there will be a lot of noise here. So 159 detections from 2 templates, let's see. Yes, this most likely is a real detection of something very, very slow magnitude, low magnitude. You see, it looks very similar to this. These two also. I don't know, and so on. But these are, I guess, these really are. This one is also an earthquake. This one also. You see, exactly the same as this. Okay, and so on. So you see, this cross correlation is very powerful method that you should use to detect many more earthquakes in the catalog you're working with. Otherwise, you may have some missing events, and the magnitude of completeness of your catalog will be much smaller than, I mean, too high, and you cannot do some very interesting work. And if I do this, what happens then? I get 20, and let's lower the trigger off time. Okay, so you see this template detector using just a small subset of detected earthquakes. We can scan our continuous data set and try to find many, many more small ones. The problem with this match filter is that normally you should work with a good network. Otherwise, you can get, let's say, high cross correlation values even for noise or for the earthquake with a different origin, especially if you filter too much, because a path. Let's say if you are working in some region in a craton, let's say in Ghana, you will have one earthquake 100 kilometers north from your station and one earthquake 100 kilometers south from the station. And if the structure between the station and the earthquake is the same, and if they have the same focal mechanism, then the signal should look very, very similar. So you need to take care with your preparation of the data set. Normally, I always try to use at least 4 stations. So I take, for each station, I generate one set of templates of one earthquake. And in this way, I can then even try to relocate these events because I will have phase peaks for these very, very small earthquakes. So this is one thing. Anything else about the match filter that you have to be? Yes, of course. So the match filter normally, let's say you take a template of magnitude 1, and using a template of magnitude 1, you can, this is, it's not really statistically shown, but this is just from the experience. So let's say your magnitude 1 template, you can find, with it, you can find earthquakes down to the magnitude 0 and up to magnitude 2. But you cannot take, let's say, magnitude 5 earthquake as a template and expect to find magnitude 0 events. So any idea why this? Does anyone have an answer? No? It's quite simple. So the magnitude 5 earthquake, the time of rupture of such event is much, much longer than of magnitude 0 or magnitude 1 earthquake. So the area that rupture is much better. So sorry, much bigger. So the waveform will look completely different than of those small events. But if you are in this ±1 magnitude window, then you can expect to detect many events that represent the template itself. So this means that the earthquake will have similar focal mechanism, it will have similar magnitude, and of course it will have similar location, plus minus few 100 meters, depend on the frequency you are using. Okay, so time for questions.
Can you come back the period window?
To this one?
Before? Before? Oh, okay. That's right. Okay. Why the sino is not continue? Because the here use you merger few value.
Merges. Mm-hmm.
Just why the signal is not continue?
So here now, when I use merge, it is continuous. Now it does not have any holes, but before it had holes. I don't know why. I mean, this is what I was able to download from the internet. So most likely, you know, there were some problems with data transfer. So not all the data came to the center, or maybe the station is not working okay. You will see this a lot of times when you download the data. So for most processing that requires continuous data sets, you need to call this merge function. Otherwise, your single day data will be, I don't know, many different small pieces. But you need to be careful what kind of this fill value you use. So this is something, you know, this is the it's the problem of the instrument, how it works or not work.
Okay, so.
And as I said, you will see this many times, this kind of problems. And if, okay, let's say for the match filter, normally I take only those data that has less than, I mean, that in 24 hours, they have at least 80% of data. If more than 80% of data is missing on that day, I do not consider this station, because then you have so many these places that you need to fill that even if you use the interpolate, you will get some, you know, values which are not actually real. And if the holes are too long, let's say a few minutes, then it's useless.
Thank you.
Yeah, so always, I mean, always with this continuous studies that require continuous waveform, you have to be really careful that the data is good quality. Because if it's not a good quality data, then you can, you know, you can detect whatever you want, and your results will not be really real. Okay, something else? No other questions? Oh, you should have a lot. Okay, then. So regarding the things that I prepared for you, this is everything. I will send you the 2 last notebooks on the emails. So now what we can do now, but we still have like half hour. Let me also put this link to the chat if someone is interested in this. Okay, so yes, as I said, next week I will start working on the exam questions for you. So I will, most likely this will be like 3 questions about what we did here during this week. So nothing out of the out of the blue. And so most likely I will also give you a few exercises that you will have to finish and send me the results. And this will be then your exam from my side. From the others, I do not know exactly what you will get, but expect more questions. So now I wanted. I told you last time during I showed you the. Just a second. Let me find the website. Yes. Okay. So for the exam, you know, you will have to download some data, maybe try to detect some earthquakes on it. Nothing hard. So everything is already here in the Jupyter notebooks. So just you get used to it. So it will not be something very hard for you to do if you just follow the already prepared Jupyter notebooks. Okay, so let me find some presentation. Okay, so I wanted to say also a few words about the low-cost instruments, because I think, you know, since you all are coming from the developing countries, it would be very, you know, it's sometimes quite easy to get some projects running if you mention low-cost devices and what you can do with them, and so on. So let me just turn this on. So yesterday, if you checked the email, I sent you a link to a presentation, I mean a kind of workshop that will take place in April. It's only 2 hours, so it will be nothing fancy. And it's in USA, so it will be at 8 p.m. Italian time. So, okay. If you want, you can attend, but you need to register, or if you don't want to, no problem. It's nothing. It will not be, you know, you will not miss a lot. But the two people that will talk, at least one is a very, I mean, it's quite known seismologist. And last year they had a very nice paper. I think I have a picture here. They had a very nice paper using seismic stations all over the world. And these seismic stations were also, some of these seismic stations were also low-cost Raspberry Shake stations. I will show you later. So they were checking this. So the talker will be this Thomas Lecoq from Belgium. And here they showed that during the COVID pandemic, you can see how noise level around the cities in the world went down. So this, what you see here on the left, are basically spectrograms of seismic stations, each in a different city. Maybe you can find your city here, maybe not. And you can see that, so each square, I think, is 1 day. So you see here, this is Christmas period, so the noise level within the city is low. And then the COVID comes and you see the drop in noise in all the cities everywhere in the world. So this is one interesting thing that people did using stations located in cities and low-cost stations located in these cities. So let's see, Napoli, this is in Italy, Milan, Catania. Is there something from Africa? Does anyone see? But anyway, you can maybe find your city here. There's also a map. So this is one is this Ghana or is this one?
Yeah, I think so.
Yes, so maybe they used a station in Ghana.
Uh-huh.
Here, no, this is Vietnam, is it?
No,
No.
Professor.
It's the Vietnam is where?
Widow.
Just this.
No, it's China.
This is in China. It's too high. Yes. Oh, I'm sorry.
Yes.
Vietnam is here.
Just.
But what now? This station is also in China, then, right?
Just.
This peninsula
Taiwan.
is just yes. This is Taiwan.
Taiwan.
So in Vietnam, no one did this. But what you can do, you can get this code here online. It's freely available, and you can try to do it on your own for Hanoi. I can put the link to this code also here if anyone will be interested in. I find it. It's how you spell this name? Thomas Lezock. So basically, all you have to do is select open station, download the data, and everything will be done automatically. So if any one of you is interested in this, you can easily do it on your own. I think I found it. Oh, this is for making pictures. Okay, I will find the code and I will send it to you. So no, it's here. Okay, I think I found it. Yes.
Thank you, sir.
You can do it for your city if the data is available. You will see. I mean, it's nice because this is something. It's something that it's very nice to show people these kind of things. Here, I put the code to the chat so you can try to run it for your own city. I tried for the capital of the city where I come from, and nothing happens. It's a small city, so even after the lockdown, there was not much difference. Okay, so this is one thing. What then there is? This is an example from they used Raspberry Shake for recording of African elephants. So you can see yes, this is acoustic sensor. So for the noise, I mean for what we can hear. And which one is? This one is for steps. You see, this is the elephant walking, and this is the recording of the elephant. So, you know, with these cheap devices, you can do so many interesting things. Let's say this is a monitoring of a landslide. In Switzerland, they put 3 seismic stations, and you can see the signal of the rockfall as it happens here. These are photos. What else? Is there something also interesting to show? This is the seismic network they installed in Nepal a few years ago using only these very low-cost devices. and they installed 25 new stations in the cities, in the villages in central Nepal. Okay, this, and let's say this is an example. I think you should know this picture from the books on seismology. So the phases as they are recorded, this is degrees away from the earthquake, and these are the recognized phases. And if you, this is the same picture done with these low cost seismic stations, and you can see that, you know, you can see even more detail in some cases. This is a recording of a washing machine that is located next to a seismic station. So you see, you can expect many different signals that not necessarily are related of earthquakes. This is rain that was recorded by the device. You see this period here does not have rain, and then a shower starts. It lasts for 20 minutes. So you have 20 minutes of rain. So you see the noise level is higher now, and then the rain stops again. This is example of aeroplane that fly over the seismic station at high velocity. So it goes faster than the speed of sound. So you can see when it's getting close to the station, because of the Doppler effect, the frequencies are getting higher faster, and then when it passes the station, you get more low frequency and the decay is slower. Okay, is there? Yes, and then let's say, why is it good to, you know, tell your institute that it's always good to maybe try to get some of these low-cost devices? This is an example of an earthquake that happened in United Kingdoms. And the station density there is not so high, but okay, it's still relatively good. And you can see that in this example, they calculated focal mechanism of this earthquake. So these are the greener stations used by local seismic institute. And you see that there is a lot of error within the focal solution. And this is the same earthquake, but now they use these low-cost devices that, you know, are owned by people that live in that area, and they share the data. So these are not by the institute, and you can now get the focal solution with much lower errors. Also, the location of the earthquake is better resolved using these Raspberry Shake stations. So this is something that, you know, people that you know, the boss of the Seismic Institute should be told, because a good seismic station will cost around, I don't know, $10,000, while these low-cost devices cost $300 or $400. It's much less, but you can get very nice results also with this. There are also many papers, few papers where they compare how the expensive, this Trillium is an expensive device, a professional one, and pink line is this Raspberry Shake cheap device, and you can see that the signal of this earthquake looks almost the same. If you zoom in a bit, there are some changes, but this is mostly because of the timing issues. So if you use a GPS together with your low-cost device, this will be better. And yes, this is how these devices look like. Yes, okay, these are just examples that I had for the citizen science school. This is the geophone inside that measures the ground motion. Okay, so this is it. So you can see these are the current stations that you can install. These cost quite a lot, and these cheap devices will look something like this, and they will give you much more detail. Okay, so Any questions? Otherwise we will finish. As I said, you can see if you go to FabLab, you can see this Raspberry Shake in action, and you can ask what's the name of the guy in FabLab. I don't remember now, the boss of FabLab at ICTP. You can ask him and they will show you the Raspberry Shake. And you can see the signal online. You can download it using OpSpy. In OpSpy, just a second, I will show you. In OpSpy, you can download any data of any station that is connected, any Raspberry Shake station that is connected to the internet. So you can check how the waveform looks like. You can go jump next to FabLab and look at the waveform in real time. And also, Simone, I think Giovanni should have one, right? So you can also try to play with.
Yeah. It's parked in the common room and it's not used, but it's there.
Oh, why? I mean, you should just put it somewhere. Put it in the campus. I mean, show them the nice paper of COVID and put it in campus. This should be done. We set 2 more Raspberry Shakes in schools in Trieste, so you can compare the signal then. Okay, so since I already mentioned the school, what you need to be careful with schools and seismic stations. So it's this is nighttime, and this is nighttime, and this is daytime. You see so much noise. This is because students are running around, doors are closing, and everything. So you need to take care. Okay. So if no one has any more questions, this is it from my side. And next week you continue with Daniel. With Daniel, I think you will look at the seismic noise tomography things. So it will be a bit more advanced, but you need to have this basic knowledge. Okay, I just wanted to tell you this, just a second. Let's try to find this. So yes, if you want to work with your own data that you can download, here on the manual of OpSpy, if you go to this client, you can see the clients that are available to get the data from. So let's say if you need to check, I mean, most stations should be available through Iris, but let's say if you want to check a Raspberry Shake station that is connected to the internet, you need, instead of Iris, you have to do this RASP Shake. Or let's say if you want Greek data, you should use something else, maybe not. If you want data from New Zealand, it's this GeoNet, and so on. So let's see. We can quickly try to see if something will work. No, this is wrong. Where is this now? Okay. Let's see. Vietnam, there is nothing.
It's nothing data.
Maybe Vietnam does not share the data at all.
I don't know. I searched before, but I don't see.
Okay, that's interesting. But you can, you can ask at your institute. They will give you the data for sure. But let's see, is there station, Raspberry station in Vietnam? No. Nothing. Huh.
Nothing.
Nothing.
Yes, because
Too bad.
because in my country we only have small earthquake in
Yes,
south.
yes, but look, Hanoi, you know,
Yes.
you see this black line here. This is a very, very big fault that if the earthquake happens here, it will not be good. Okay, anyway, I mean, maybe Karim will tell you something more about this. I think it's called... Yes, this is, check here, Red River Fault. It's one of very fast faults, actually. So, see, it was responsible for this Tonghai earthquake in northern... this is, okay. This is still China, but...
It's from China.
Yeah, but look, it was a magnitude 7.1. And this goes directly through Hanoi.
Maybe, Professor.
You know, everyone lives on a fault. So even here in Trieste, you are never safe. There is many faults around. So, okay then. If no one has any questions, we can finish. And okay, so I will send you the 2 Jupyter notebooks, and if any question arises, please send me an email. I will answer, and I hope that we can see each other soon. I will try to get to ICTP, but currently for our country doesn't look too good again. So.
Okay, Professor, thank you.
Yes. Okay, enjoy the rest of the day and see you.
Professor, I have
Yes.
a question.
Bye.
Sure.
How can I speak your name? It's special.
My
It's
name?
Blaž
Yes.
Vicic. Vicic.
No.
Am I wrong?
Yes, you are. It's Blaž.
Oh, really?
Blaž
Okay.
Vicic.
Blood physics.
Okay.
So my first name is Blaž.
Just
Okay. So it was a pleasure.
because I see some special symbol.
Yes. These are
like
the characters in our alphabet.
it's
Yes.
from the country.
Yes.
Thank you.
Yeah, no problem. Okay, so it was nice to give you the lectures, and
Thank you.
maybe some of you will decide for final work to be done something with earthquakes. Then I guess you will work with me. If you decide to do something else, there are other people.
We hope. Okay, Professor.
Okay, so enjoy and see you.
Okay, bye.
Thank
Bye.
you so
Thank
much.
you.
Yeah, no problem. Bye.
Bye.
Hi, Tufek. Tufek, are you here? Hey, Tufek. Can you hear me? He went, Tufek. He's not there.